Hello! In this video we will talk about the laser rate equations. The nice thing about the rate equations is that at least in a steady state solution we have very simple mathematics which will describe really fundamental elements of the laser and thus will enable us to understand how a laser works very good. As a final result of this session, we will derive an equation which gives us the laser power directly independent of the pump power with which we feed the energy into the system. We will take a look at 5 points. To start out with some motivation, we will talk about elementary processes of light-matter interaction. Then we will analyze the rate equations, the 3 and 4 level systems, and finally we will move on to the situation when we set up the rate equation for an optical resonator, which means now that we have the 2 mirrors selecting the modes in which the laser later on will start to oscillate. Finally, as a result, we will have an analysis of the laser power curve, that is the dependence of the laser power on the pump rate and pump energy. So to start with, we will take a look at the elementary processes of light-matter interaction, and as an example we displayed here the simplest atom we can think of, an hydrogen atom. And what you probably know is if we put some energy into the system and excite an electron which is here in the ground state, then it will move up to a higher state of excitation. And finally, the excited atom relaxes under the emission of a photon. So let's take a closer look at the processes of emission and absorption of light as an example. So we'll start with the absorption of light and think of an arbitrary light source with a constant frequency in the emission characteristic, and we shine this light into an absorbing medium, and what we observe is that at individual frequencies we get absorption of different intensities. The other hand, if we look at the emission of light, let's think of a thermal light source like the sun, and you all know that this is described by the Planck curve of radiation shown here, the spectral emission, so the intensity as a function of the emitted frequency has its maximum here, which depends on the temperature of that thermal radiator, and in this case we will have a continuous spectrum. However, if the medium is not solid but if it's a gaseous light source, which is in thermal equilibrium, then we will see the individual lines of emission, so the atomically allowed lines. However, the envelope of the emitted intensity again will follow Planck's equation. Now, if we take a look at the laser as a very elementary process, the amplification of light, then think of a rather narrow distribution of frequencies, so maybe just a very small band, and we put this light into a medium, and in this medium we excite the medium such that we get an amplification of the induced light, and as a result we will have an increased intensity, however with more or less the same spectral width of the light source. So to these processes you are more or less familiar, and what we will do now is take a closer look at the individual energy levels in these processes and how they are populated and depopulated due to the characteristic processes of emission and absorption of radiation. In this next view graph you see 2 energy levels denoted by E1 and N1. E1 is the energy and N is the number of electrons in this state, or rather the number of atoms with electrons in this state. And number 2, the energy level number 2, is denoted by its energy E2 and the corresponding number of atoms or molecules in this state. If we now shine light into that system, we excite one of the atoms with the incoming photon from the ground state to the upper excited state. And if we now count the number of states, then we observe that N1, the lower energy level, will be depopularized by a factor which is proportional to the number of photons coming in. The more photons come in, the higher the change rate of level 1 will be. And of course it will also depend on the number of atoms or molecules in that state. And the factor B12, which you see here, actually takes care of the rate, how this happens. So it's something like the cross-section of the reaction, a rate constant, as we also call it, which is depending on the medium. If you do the same thing for the upper laser level, the upper energy level, then we get the same term, however now with a positive sign, because all the states which are depopularized end finally in a state of population of the upper energy level. And the number of photons, if we count those over the time, we get again the same rate, however now negative, because all the photons which contribute to the absorption are absorbed, and thus the development in time of the photons is negative. Now if we have a depopulation of the excited state, and thus as a consequence the emission of a second photon, then the stimulated emission will be proportional to the number of atoms or molecules in the upper state, to the number of photons which stimulate this emission, and again the rate constant which defines the rate. And if we count the number of atoms or molecules in state 1, this is of course a positive contribution, because now with the relaxation the electron moves from the upper state to the lower state. And on the other hand, for the atoms or molecules in the upper state, this will be a negative contribution, however, of the same term. And again, for the photons which now are generated, we have also the same term, however now positive, because we generate the photons from the excited atoms or molecules. We have to consider one more process besides the stimulated emission, that is the spontaneous emission, because of course these excited atoms or molecules can relax without the stimulation of an additional photon. And this is displayed here, and the corresponding rates which we now have to add to the change of N1, N2 and Q are proportional in the upper state to N2, and the rate constant for this spontaneous emission is called A to 1, from 2 to 1. It is not the same as B, because B is for stimulated emission, and now we do not have the participation of a photon. So it's obvious that A has to be a very different value. So, and as a result, very simple, we have a positive contribution to N1, because this is populated. We have a negative contribution to N2, and of course the photons get emitted, so also the contribution to the photons is positive. I would like to open a little bracket and give you a little more in-depth information on the rate coefficients A and B, which also are referred to as the Einstein coefficients for stimulated and spontaneous emission of radiation. If we do so, you see here these Einstein coefficients. For symmetry reasons, B21 is exactly the same as B12, and A21 is of course only meaningful from the second to the first level, from the upper to the lower level, because there's no spontaneous absorption of photons. So in a more common formulation, which you see displayed here, we don't use numbers of molecules or atoms and numbers of photons, but we rather use the densities. So all the dimensions change, and the Einstein coefficients, B for stimulated emission, usually then have the dimension of per joule meters cubed per seconds square. So just as a further information, if we look at the elementary processes of absorption, stimulated emission, and spontaneous emission, the easiest to describe is the absorption, where we just need classical theory in the electromagnetic field as well as in the description of the matter. If we look at stimulated emission, we need a quantized analysis of the matter, in this case the quantized atomic model. And if we want to describe spontaneous emission, we also need to quantize the electromagnetic field in order to describe this phenomenon. If we now look at real systems, usually we differentiate them into 3-level systems or 4-level systems. And we will take a little closer look into one of these systems in order to understand what's happening. For example, the 4-laser level laser medium. In this case, we have 4 states. We have a ground level, in which all the atoms or molecules of our active medium start. Then we have a pump level. This pump level is above the upper laser level, because most of the energy will be absorbed by the medium such that we will populate not only the upper laser level itself, but also levels above that, which then relax to the upper laser level. Then we will have the laser process to come back to the lower laser level, and from there the relaxation starts back to the ground level. Visualized, you see here the absorption from the ground state to some pump level, then the going back from the pump level, the cascading to the upper laser level. This can be happen by thermal energy creation or by collisions or also by radiative processes. So we populate finally the upper laser level. From there we will then have a emission to the lower laser level. If it is stimulated by an incoming photon, we talk about the stimulated emission, and from there the relaxation back to the ground level. All in all, we come in with a photon, have an excited upper laser level state, and generate from this, with the transition, the second photon in order to provide the amplification of the radiation field. Now, that is the 4-laser level system, and if we now ask how can we select the direction of stimulated emission, we put the whole thing into a resonator. And this resonator is characterized by the 2 mirrors, as you know from the resonator video. And in this case, then we have a back and forth reflection of the photons in a specific direction, which allows us to have more and more photons to stimulate the process, and thus generating the laser by amplification through stimulated emission of radiation. We furthermore, in the rate equations, have to consider 2 aspects. One is the resonator decay constant. If you look at the resonator itself, then of course we take out some of the laser energy, and this happens with each round trip, and we call this loss factor for the resonator itself. The outcoupled laser beam is to be considered like a loss factor. We call it beta. And another aspect we have to take into account with the resonator is the so-called resonator selectivity, which is displayed on the right of that picture, due to the fact that we cut out of the full solid angle only a relatively small angle delta omega. We need this factor delta omega in order to select only those photons which are emitted spontaneously in the direction of the resonator mirrors, because the others, which may be emitted spontaneously in other directions, do not contribute to the number of photons in the resonator itself. A little more detailed view on the resonator selectivity f omega gives us a feeling of the magnitude of that number, and it turns out to be very small. For typical data of a resonator which are put in here, we come out with a number of something like 10 to the minus 4, 10 to the minus 5. So it's a very small number which we have to bring into the equation in order to describe only those photons which are emitted spontaneously in the direction of the resonator. To come back to the resulting rate equations now, they are displayed here. We can see that the solid angle contribution of the spontaneous emission is respected here in the number of photons counted, and also the number of photons coupled out per second, beta q, is recognized in the equation for the photons. One more thing, in the 4-level system we have to take care about the depopulation of the lowest energy level N0, and this of course is the inverse of the pump rate. So the higher the pump rate, the higher is the depopulation of the ground state. So those are finally the rate equations, and if we analyze them and take a look at the ratio of the number of photons generated stimulatively versus the number of photons generated spontaneously, then we observe a very simple equation, and this equation tells us that number one, if we have effective cooling, then the laser level N1 will be small and we will have a high inversion, and by inversion we mean the difference of the upper laser level to the lower laser level N2 minus N1. So if N2 minus N1 gets large, the stimulated emission of photons will dominate more significantly. So higher cooling, higher number of laser photons. The second thing is, if we use a high pump rate, then we get a higher population of the upper laser level, N2, which again leads to a higher population inversion. So we want to pump hard. And number three is that in the equation you see a direct linear dependence on the photon number. So the more photons we will have in the resonator, the more the stimulated emission of radiation will dominate the generation of photons. So this was actually all about the rate equations. In the remaining minutes of this video, we will simplify and analyze the rate equation in steady state for the description of the laser power. So if we further simplify the equations, number one, what we look at is that with increasing population of the upper laser level N2, we can substitute the difference of population N2 minus N1, the inversion, simply by the number in the upper laser level N. Also, if we look at the ground state, then the ground state population, which basically comes from spontaneous emission from the lower laser level, usually is large compared to the pump rate, so we have a very quick depopulation of the lower laser level and then a corresponding pumping out of that ground state. With these simplifications, the rate equations become even simpler, and we now only are left with 2, with one for n, or the inversion, the population inversion, n, and on the other hand, the photon number q. A further simplification is displayed in this next picture, where we now introduce new definitions. They are shown here on the upper right-hand side. We normalize the numbers and get dimensionless quantities. So now n bar is equal to n, however, multiplied by the ratio of the Einstein coefficients b and a. The same thing for the photon number, and for the pump rate we introduce essentially the same ratio, however also include the beta in this new definition of the coordinate. So ultimately the 4-level rate equations take the form in the dimensionless writing, which is displayed here, and this is actually very simple. It's only 2 equations and we can analyze them. The first thing we do is we look for the solution of the stationary state. In the stationary state, of course, we set the time derivatives to 0 and result with a very simple quadratic equation, basically quadratic equation for the dependence of the number of photons on the pump rate. The only parameter in here is the f omega, which we have learned already is usually very, very small. Now, if we analyze the equation and solve it, we find 2 cases, one in which p is small compared to 1, and one where p is larger than 1 or larger equal 1. Then we get different parts in the solution which contribute to the value of q, and this is displayed here. So it turns out that at p equals 1 we will have the laser threshold. So for values under the threshold we will have a 0 photon density in the beginning. However, the population inversion will increase linearly with the increase of the pump rate. At the laser threshold, the population inversion, here in green, will go into saturation, and with this effect the creation of photons by stimulated emission will start, and it will increase in this very simple model of rate equations linearly with the increase in pump power. If we take a closer look of what happens in dependence of the f omega, if we set the f omega, so remember this is the spontaneous emission, equal to 1, so we recognize all photons emitted in the full solid angle, this is more or less a black body situation, then we have a very strong dependence also for pump rates under the threshold of the laser. However, for realistic f omegas in the range of 10 to the minus 4 to 10 to the minus 6, you see these curves get very close to a steep increase at the laser's threshold, p equals 1. And if we magnify this region here, you see the picture on the right, and it tells us that with very small changes around the laser threshold, which is p bar equals 1, we get significant changes in photon numbers, in this case here, between, remember, look at, this is a logarithmic scale, 10 orders of magnitude. So at the laser threshold, very small changes of the pump power will result in significant changes in the production of stimulated photons. 10 orders of magnitude are the usual numbers. This effect actually can be compared to a second order phase transition. To remember, a first order phase transition is, for example, the melting of ice. You are all familiar that if we increase the temperature by putting thermal energy to a system, then the temperature will increase in a solid state. However, when the material starts to melt, the temperature will not increase further, but we will have a jump in the need of contribution of thermal energy, which is the latent heat we need to put to the system. Here, if we differentiate the thermal energy curve versus the temperature, it is not steady. We have a jump in that picture here. In the laser transition, the dependence of the number of photons of the pump is continuous. However, it shows very steep changes around the threshold, as said before. Finally, to give you an example of how these rate equations can be applied, here you see a characteristic, as we call it, of a diode laser. So these diode lasers depend in their output laser power on the electrical power which is put in, and with increased electrical power input we get increased photon numbers. And you see the behavior as described by the rate equations. In the beginning, of course, we have 0 up to a certain threshold, and from this threshold on we have a linear increase of the number of photons as shown in the blue dotted curve. In reality, we have some difference, some deviation from that, which is due to thermal effects in the active medium and to resonator instabilities in terms of the density of the excited states in the semiconductor, which tells us we need more complex models to describe this behavior. So, as a result, we now have a rather simple model to describe, at least in a stationary state, the dependence of the number of photons on the pump intensity. And the result is, under the threshold we have no photons, over the threshold we have an increase in, a linear increase in photons under a saturated population inversion. The population inversion remains constant if we operate the laser. In more detail, you saw the deviations from the model in the real case, and for descriptions of these deviations we need to take into account thermal changes of the active medium and also instabilities in the local homogeneity of the pump power in the active medium, which makes it then more complex.